So let's take a look at this question. It says the average body temperature for healthy adults is. Whenever you see the word is in math, that means equal. So is 98.6, and that's good to know. Whenever you see the word is, that means equal. Is this statement true? Do all healthy people have exactly the same body temperature? Or could they be below or above? And that's why, my alternative hypothesis is not equal. So we're looking to see, do they actually have a difference? And they give me some information here. They say the body temperature, so they give me a sample. They went out and took a sample of 130 healthy adults. So that's my sample size. The average temperature, so the average sample mean was 98.249 with a sample standard deviation of 0.7332. All right, so what we're looking at to see is, do we believe what they're telling us? And right away, draw a picture. Draw a picture, draw a picture, draw a picture. What do you draw a picture of? Normal curve. Right down the middle is what they're telling us in the null hypothesis, is that the average temperature is 98.6. We want to know is 98.249, which we already can tell just by looking at that, it's going to be to the left. But we basically are looking to see, is that too far away from the 98.6? All right, so we're looking again, as I mentioned in my lecture, that we're looking, is there a significant difference? So what we have to do is we have to standardize our mean to 0, and we have to figure out what this value would be, okay, our test statistic, because that way we can look up probabilities that we would expect to get this sample based on what they're telling us the average temperature is. And in this case, we only know the sample standard deviation, so my test statistic's going to be a t. Remember, all of these, you take the sample minus the population, and then over the standard error, which in this case is the sample standard deviation, divided by the square root of n. All right, so if you just plug in these numbers, the 98.249 minus 98.6, all divided by the 0.7332 over the square root of 130, that is going to give me my test statistic. Now, this problem did not give you, which normal problems would, an alpha. In other words, remember, alpha is my cutoff region. So let's say that my alpha is here. Okay, I don't know, but if it's here, then if that value fell in that region, then I would say, no, we're kind of rejecting the null that the average body temperature is 98.6. If my critical value ended up being here, then all of this is my critical region, and then this does fall. Okay, this actually does fall in the critical region, and so we would reject. Otherwise, if it doesn't, then we would say, no, we really don't have enough evidence to state that the average body temperature is not 98.6. All right, so this should kind of get you started that you need to find that t statistic, which most have already in the discussion. Just say, if we used an alpha of 0.01 or 0.05, I think you're going to see, regardless, it doesn't matter the normal alpha values that are picked, what you pick. The other one is 0.10. You're going to find the critical value, you're going to look this up in the t table, and or, as I say in my lecture, you can get a p-value, which says the probability that I would expect to get this value in a sample if what they're telling me is true. So this should at least definitely get you where you understand the picture, all right? Because all of these you should be drawing a picture, that you actually understand the picture. In this case, this is actually a two-tail test, so your critical region is going to be on both sides. It's just we're kind of concentrating on the left-hand side because this sample was on the left. But you need to remember, when you have a two-tail test, you are cutting off two tails. All right, so hopefully this is enough to kind of get you started and get in there communicating, and listen to my live session to see how to find that p-value, because I think you'll see that's a little easier to decipher than the looking up a critical value.